Alright, students, it's time to take a look at the topic 2 and 12 test review multiple choice solutions. I know you had fun answering those questions. Let's see how great you did. Here's the first section. Question number 1 says, which of the following particles contain more electrons than neutrons? So I think the real trick for each one is to figure out how many of each we have. For hydrogen, atomic number 1 and a mass number of 1. The atomic number of 1 will tell us I have 1 electron. And since my mass number is 1 and I have 1 proton, that means I have 0 neutrons. So this already is one of our correct answers. The next one we have to look at, mass of 35 and atomic number of 17, is chloride. I call it chloride because it has that -1 charge, right? Well, if I count up electrons on this, I have 18 electrons, 17 to match the protons and 1 extra. And if I subtract my mass number, my atomic number from my mass number, I get 18 neutrons. So this one is equal. So number 2 is not an answer. So we know number 1 is correct. Number 2 does not work. The only choice in here that has 1 but not 2, well, that's not the menu pop-up I wanted there. It's letter A. We can double check potassium just for fun. Potassium with a +1 charge. Normally it would have 19 electrons, but the +1 means we've lost one, so we have 18 electrons. And the difference between my mass number and atomic number there is 20 neutrons. Definitely no good. Pretty comfortable with our answer of A there. Question 2 says the atom with the same number of neutrons as chromium-54 is, well, for this one we've got to hit up the old periodic table, which is no problem. We have to hit up the periodic table because although we have mass numbers, we also need atomic numbers. So chromium with 54 for a mass number, we find it on the periodic table, has 24 for its atomic number, which means 30 neutrons. Any of the others with 30 neutrons, we can find out here. So titanium, Ti, with a mass of 50 and 22 for its atomic number. That one, if we do the math there, is only 28 neutrons. So nope, titanium doesn't count. V for vanadium, or Vedetta, or whatever, depends on your movie buff happiness here. Has an atomic number of 23. That gives us 28 neutrons in there. Nope. Iron. Man. Alright, mass of 53, and iron is atomic number 26. And 53 minus 26 is 27. Still don't have the same number of neutrons there. Dun dun dun. Could any of them? Let's find out about manganese. Manganese with a mass of 55 and an atomic number of 25 means 30 neutrons if we subtract. Good news, letter D is the answer. Now, next part has to do with the definition of isotope. All isotopes of tin have the same number of protons. Well, we know that's true because an isotope is the same type of atom, and all tin will have the same number of protons. Number of neutrons? No way. That's what makes an isotope an isotope. It's a type of atom that has a different number of neutrons. So definitely no on number 2 there. And mass number, well, if they have differing number of neutrons, we're going to have a different number of, or pardon me, a different mass number. So letter A is our best choice there. Which of the following sets represents a pair of isotopes? Remember our definition of isotope. They have to have the same number of protons, but differing mass numbers because of different numbers of neutrons in the nucleus. Letter A has 2 different atoms, 6 and 7, for their atomic numbers respectively. That means they can't be isotopes. O2 and O3, look where these subscripts are written. These indicate molecules. I've got 2 atoms combined here and 3 atoms combined here. It's not an isotope. This one's promising. We have the same number of atomic numbers in letter C for the 2 sulfurs, 16 and 16. But if you notice, the mass numbers are the same in both. One of them has no charge and the other does have a charge. That means we have an atom and its ion, not 2 isotopes. Process of elimination, letter D is correct. And we can take a look. Those 2 samples of lead both have a mass number that are different, 206 and 208, while having the same atomic number of 82. So far we're doing great. Number 5 says the atomic and mass numbers of 4 different nuclei are given in the table below. Which two are isotopes? Well, remember, in order to be isotopes, they have to have the same atomic number. Go away, little window. There we go. Same atomic number. That's numbers 2 and 3. That's all we need to know about that. We could compare their mass numbers and notice those mass numbers are different. That's okay. That's what makes an isotope an isotope. For question 6 in your assignment, it said which species contains 16 protons, 17 neutrons, and 18 electrons? Well, we know it's sulfur. That's atomic number 16. That part was easy. If I add 17 to that, I get 33, right? Let's check my math. 17, yeah, 33. Good job, Mr. Kilmer. All right, so 16 and 33 up there. We can take a look at our options right now. Oh, look at this. Boom. B is the only one that seems to have the right mass number to begin with. We can also look at the idea of 18 electrons. That means I've got 2 more electrons than protons. So that gives me 2 extra negative charges. That part's right. Number 7 talks about emission spectra. And emission spectra are some of our big evidence that electrons move from higher energy to lower energy levels, with the energy levels being close together when they're far away from the nucleus. Higher to lower energy levels, with the higher energy levels being closer together. Ding, ding, ding. And it has to do with the frequencies of light emitted. D is our best answer there. Which electron transition in the hydrogen atom releases the most energy? Remember, to release the most energy, you're going to have the greatest fall. So we want a big jump here. Which one's going to be the big transition? Well, looking from level 6 to level 3, that's 3 levels. A has 2 to 1, that's one level jump. B is 2 level jump. C, I think, is going to be our best bet. It's going to release the most energy. An element has the electron configuration of 2, 7. Remember, that's more of an electron arrangement, really. What that means is that our level 1 has 2 electrons, and our level 2 has 7 electrons. What would be the electron configuration of an element with similar chemical properties? Chemical properties are determined by the valence electrons, the number of electrons in the outer level. In this example we're given here, 7 right there tells us our valence electrons. This one also ends in 7, so it's going to be our best match. It's tempting to look at this one, saying, oh, it's got the 2 and 7 as well, but the valence electron here is 1, so it's not going to match this one with 7 valence electrons. This family happens to be chlorine, fluorine, bromine, iodine. Question number 10 says an element with the symbol Z has the electron configuration 2, 8, and 6. Again, more of an electron arrangement. Which species is this element most likely to form? All right, so its symbol is Z, and if it has 6 valence electrons, that means it's only 2 electrons away from gaining a full outer energy level. So this is likely to form a -2 ion if given a chance. It'll pick up those 2 more electrons. And if that's the case, we can eliminate A and B. Now my next option here says that I could get 2 hydrogens combining with that. Well, we know that hydrogen each has a +1 charge, so 2 hydrogens would match up very nicely with that. I think C is our best choice. Element D is not as likely at all, because in this case this shows Z being a positive ion, meaning that it's lost electrons. It's easier to gain 2 electrons than to lose 6, and if this were going to form, we would have 6 fluorides, not 6 Z's, whatever that Z happens to be. Question number 11 uses this little diagram. This is the sort of readout we might get from a mass spectrometer that shows us abundance with mass. Now you'll notice in this case we don't have any numbers for abundance, so we're just going to have to use the height of the lines to make some decisions. It says according to the mass spectrum above, the relative atomic mass of the element shown is best expressed as, well, it's going to be an average of these 3, but it's not going to be 21, which would be the dead center average, right? because we have a lot of 20 and very little 22. As a matter of fact, that kind of weights our average closer to the 20 than to the 22. So I'm going to have an average atomic mass somewhere between 20 and 21. It's not going to be between 21 and 22 because there's so much more of the element with a mass of 20 than with a mass of 22. The next one talks about ionization energies, like the lab you've been working on. It says the first 4 ionization energies in kilojoules per mole for a particular element are 550, 1064, which is a doubling of energy. But then look at this, going from the second to the third, that's 4 times as much energy being taken out almost. Or that is required, pardon me, to remove that extra electron. So removing 1 was pretty easy. 2 was a little tougher. 3 was a lot tougher. And then 4 is pretty close. It's really not a lot of difference between 3 and 4, or 1 and 2, which indicates that right here is where we have a energy level being broken apart. We've dropped down closer to the nucleus. B is our best bet. Beryllium, being a group 2 element, has 2 electrons in its valence level. The first one would be fairly easy to remove. The second one would take a little bit more energy, but then breaking down into that level below would be pretty tough. Yeah, I think this is probably our best bet. We've got a couple other little tricks here. For example, it can't be lithium because lithium is atomic number 3. It only has 3 electrons, so no good for that. The others, well, possible. I still think beryllium's our best bet based on that huge jump in energy difference between removing the second and third electron. Last 3, you can do it. Which ionization requires the most energy? Remember, trying to break down to a level closer to the nucleus takes more energy. For letter A, sodium has 1 valence electron. Taking that away is not going to be that tough. But getting that second one that would come out of level 2p, that one's going to be really tough. Magnesium has 2 valence electrons. It's not going to be tough to take away the first one or even the second one because we're not breaking into a level closer to the nucleus. I think B is our best choice. It's the only one that has us pulling an electron from closer to the nucleus. Number 14, which of the following atoms in the ground state has the greatest number of unpaired electrons? For this one, we just have to draw the electron configuration of each and compare. Looking at these arrangements, we can see that aluminum has 1 extra electron, at 3p1. Silicon, although it has a 2 that's an even number, it seems like a pair, but these are 2 singles. Phosphorus has 3 singles in that p level, and sulfur has 2 singles and a pair. So the one with the greatest number of unpaired electrons, that's phosphorus. Number 15, all of the following factors affect the value of the ionization energy of the atom, except, remember, ionization energy is the amount of energy required to remove that outside electron. The size of the atom, which indicates the distance an electron will be from the nucleus, plays a role. And the charge of the nucleus plays a role because that determines how many electrons there will be. The main energy level from which the electron is removed definitely matters because that's a decision of whether we're taking an easy to remove or a closely held electron. The mass of the atom is the part that doesn't play much significant role. Although there are gravitational attractions between the nucleus and the electron, they're incredibly small compared to the electrostatic attractions between them. So letter A is our best bet there.